Exercise 2317 is trying to get us to think about reductive amination from the perspective of a multi-step synthesis exercise. So we can take this, this process that we want to achieve, and we can think about how we could create this product from this reactant, maybe somewhere using a reductive amination. Now, if you're thinking about a reductive amination, a place to start is to notice that you have an amine. And if you have an amine, that amine can be formed from an aldehyde or a ketone. So you could say, I could make this molecule if I had, and you draw the retrosynthetic arrow, and you would copy the same thing, the same molecule, but where you have the amines, you would separate them, so remove the amines off of the molecule, and where they were, you would introduce carbonyls. So you could have, for example, a carbonyl here, and you would have a carbonyl here. If you had those carbonyls, then, and wherever they were on the hydrogen, or wherever the nitrogen was bonded to those, you introduce a hydrogen. So we've seen that procedure before in the videos practicing one-step reductive aminations. But if we had this aldehyde ketone molecule and these amines, we could put them together, do a reductive amination in the presence of catalytic acid and a weak reducing agent like sodium cyanoborohydride, NaBH3CN. That would turn into the amine that we want, or the diamine that we want, this molecule with two amines on it. Okay, that's fun. But if we look at this and we compare it with our original molecule, it does not resemble it very much. So maybe that's a nice idea, but maybe it's sort of a dead end. Well, let's think about it. If you ever get stuck going in one direction, like here we were doing retrosynthesis, working backwards, try working in the other direction. What we have here is an alkane. And as we've seen already in this chapter, and that an idea that you should have been introduced to in Organic Chemistry 1, is that there are very few reactions you can do with alkanes. One is you can light them on fire and get energy and carbon dioxide. It's the reaction you use when you breathe, or like you exhale, the carbon dioxide you exhale is happening because you're turning hydrocarbons into carbon dioxide. That's also the reaction that happens when you run your car and the gasoline is burned, or when a candle burns, or when wood burns. In all of those cases, an alkane is getting turned into carbon dioxide and energy. But that's not going to make us produce these molecules here. It's not going to let us produce those. So instead, we'll have to use the only other reaction that you can do with these alkanes, and that's a radical reaction. If you treat the alkane with N-bromosuccinimide and light, and the mechanism for this are in multiple videos that I have for Organic Chemistry 1, so if you're interested in those, I can send those to you. But if you do that radical reaction on this alkane, the result is that you will add a bromine onto the most substituted carbon in the molecule. That's the carbon bonded to the most carbons. So this carbon here is tertiary, it's bonded to 3 other carbons, and that's more substituted than any other atom is in that molecule. So that's where the bromine is going to add. Now we did that because that's the only thing you can do with alkanes. But when we get that, it still doesn't look very similar to our product. Well, one thing I do notice is that although we have a bromine here, we definitely don't have a bromine in the final product. So we will have to get rid of the bromine. In other words, we have to do an elimination reaction. Now, in the context of elimination, the carbon that has the leaving group on it is called the alpha carbon, and each of the carbons next to it are called beta carbons. So we could do 2 possible eliminations here. We could do one elimination where we use a bulky base, like potassium tert butoxide. And that bulky base will only be able to steal a hydrogen from the least crowded beta carbon. So in this scenario, potassium tert butoxide, which looks like this, The negative oxygen there would be able to steal this hydrogen, the electrons go toward the leaving group and kick the leaving group off. And you would form, in that scenario, you would form an alkene in the direction of the beta hydrogen that got stolen. So that's one possibility. Okay, another possibility is we could use a skinny base. So a skinny base like sodium hydroxide, or sodium methoxide, or sodium ethoxide. If we do that, a skinny base, and here I'll use just sodium methoxide, so you have a methyl group bonded to an oxygen. The oxygen has a full negative charge, and a sodium is there to help balance out that charge. But that can steal a hydrogen from a more crowded beta carbon. Now notice that there is a symmetry in this molecule. The left and right, or the top and bottom halves of it are the same down this line here. And so whether I steal it from this beta carbon or the other beta carbon amounts to the same thing. Ultimately, your base steals the hydrogen, the electrons go toward the leaving group and kick the leaving group off. So you end up forming an alkene in the direction of the beta hydrogen that you stole. So this one here. You kick the leaving group off, and you end up forming a pi bond here. Okay, now I'm going to erase all these alphas and betas so that they don't distract us. These are our two possible products. We could make either of them, just whichever one would be useful. And what we have at this point are alkenes, but what we want are carbonyls. There is a way to turn alkenes into carbonyls. You learned it in Organic Chemistry 1. It was ozonolysis. If you treat an alkene with ozone in the first step, that's O3, followed by a reducing agent, dimethyl sulfide, DMS, so that's sulfur with two methyl groups on each side. So dimethyl sulfide, DMS, what you end up doing is breaking the double bond and where you had it, the carbons on either side still have a double bond, but they are to the oxygen from ozone. So those ozone oxygens are the oxygens that form these carbonyls, or that get incorporated into those carbonyls. So that's what we would get if we did ozonolysis with that one alkene that we could make. If we do ozonolysis to the other alkene we could make, we would break this bond, so that we could erase it, and where the double bond to the between the carbons was, we can have two double bonds to oxygens, so carbonyls. So we'd have those two carbonyls there. And now, if you compare this product to the product we wanted, almost miraculously, it looks the same. Or at least it looks a little similar. We have a carbon chain with two carbonyls on it. Let's see if it is the same. Let's number this and draw this in a more normal way. We have 1, 2, 3, 4, 5, 6, 7 carbons. 7 carbons. So what if we have 1, 2, 3, 4, 5, 6, 7 carbons? And I'll number these just so we can keep track of them better. On carbon number 1, we would have a carbonyl. And on carbon number 6, we would have a carbonyl. Well, notice that that molecule is exactly the same as this molecule here. These two are exactly the same. And so we've devised a way to get that dicarbonyl there, that aldehyde and ketone on the same carbon chain. So this procedure on the left, that was a dead end. That didn't lead to anything useful. So instead, we would, at this point, after we get this, our alkyl halide, the only thing we can make from just a regular old alkane, after we get that alkyl halide, we will want to treat that alkyl halide with a skinny base like sodium methoxide. You can also use sodium hydroxide or sodium ethoxide. That will give you the alkene, and you can do ozonolysis on the alkene to get this carbonyl compound. And once you have that, well, then you can add the amines and do the reductive amination. Okay, so let's review this from the top. We have an alkane. The only thing you can do to an alkane is a radical reaction, the only useful thing. The other thing is you can burn it and get carbon dioxide. So we can use N-bromosuccinimide in the presence of ultraviolet light, and that will turn this molecule into a haloalkane. Halogens are windows to the world because they're good leaving groups. After you have them on the molecule, you can do substitution and elimination reactions. We noticed that our product did not have a bromine on it, and so we thought, let's do an elimination. We thought about the Hoffman and the Zaitsev elimination, the elimination reaction toward the more substituted carbons, or toward the more crowded or the less crowded carbons, and we decided that to get the product we wanted, we needed to use a skinny base like sodium methoxide. That gave us a product with a double bond. Once we had that, we saw that we could break it apart by doing ozonolysis. So first we would treat this with ozone, and then we would treat it with dimethyl sulfide. That would cleave the double bond and give us this molecule here. And actually I could copy both of those so it's easier to see. So those are the same. This way is drawn so that you can see the effect of the ozone on that bond, breaking it and replacing it with two carbonyls, and this is drawn in a more normal way, or a more conventional way. And once we have that, we could treat it with two equivalents of the amine that we want. So that was a nitrogen with two methyl groups and a hydrogen. So two methyl groups and a hydrogen. We could use catalytic acid and sodium cyanoborohydride, NaBH3CN. That will do a reductive amination that will replace those carbonyls with amines, the amines that we added. So we'd have two equivalents of this amine, and that would replace the carbonyl with the amine. So nitrogen, two methyl groups. Nitrogen, two methyl groups. And that was the product that we wanted to make. So if we go back up here and look at it, that is the same molecule as this one here. Now, it looks a little bit different because the single bonds can rotate, but you'll see that if we number these, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7. We have 7 carbons long. On carbon number 1, we have this nitrogen with two methyl groups. And on carbon number 6, we have this nitrogen with two methyl groups. And so you could see that these molecules are the same. So overall, if we were just listing the reactions we would need to do, first, it would be NBS and light, so NBS and H nu. Second, we would need sodium methoxide. Third, we would bubble ozone through there. Fourth, we'd reduce that with dimethyl sulfide. And then fifth, we would do the reductive amination with 2 equivalents of dimethylamine in the presence of an acid catalyst and a weak reducing agent like sodium cyanoborohydride NaBH3CN. And that beautiful artistic process would allow us to create this transformation.